Dear colleagues, I am Всеволод Bogayenko from the Institute of Cybernetics in Kiev, and I am pleased to have an ability to present the talk on parameters identification for fractional fractal model of filtration consolidation using GPU. I would like to start from some general context. We study mathematical modeling of transport processes in Polish media on the basis of the models of non-integer order. Such models contain integral differential operators, the so-called fractional derivatives, the order of which usually do not have some precise physical meaning and cannot be instrumentally measured. To practically use such models and other models with the same properties, we should solve inverse problems of determining such values of non-measurable parameters that allows describing measurable indicators of processes dynamics with the best possible accuracy. For complex underlying mathematical problems, including initial boundary value problems for integral differential equations, the efficient class of methods used to identify the values of their parameters is the class of population-based meta-heuristics methods. Their working principles include the solution of independent series of direct problems that makes possible an easy application of parallel computing techniques for shared memory systems for their implementation. Talking about the results, I will start from the direct mathematical problem. We consider the system of fractional differential equations that describe non-local mass transfer and consolidation processes in soils of fractal structure. This system contains the non-local fractional derivative of Caputo type with respect to the time variable and the local fractal derivative with respect to the space variable. They determine two parameters, the orders, respectively, of the model that need identification on the basis of available measurements of water head and salt concentration, considering the values of other physical parameters that are known. We pose an initial boundary value problem for this model, adding a first-order condition to it, and solve this problem using a finite difference technique. The example of the dynamics of the process described by the considered model is given in the current slide. Comparing to the case of classical models that contains derivatives of integer order, this non-classical integral differential model describes the processes in which the dissipation of water heads and the distribution of salt concentrations have non-symmetric features and different states. So, we look for a computer science solution in the situation when the observed process visibly differs from the expected classical behavior and its dynamics should be modeled using a generalized fractional model with non-measurable parameters. We assume that there are a set of measured values of process indicators, in our case water heads and salt concentrations, on known depth and in known time points. We define a goal function as a sum of squares of differences between the measured values and the modeled ones, and propose to use particle swarm optimization algorithm to find the values of non-measurable parameters. Briefly, a fixed set of particles whose coordinates corresponds to the fitted parameters move iteratively in a force field with intensity that depend on goal function value. In our study, we use the basic version of PSO, focusing on its accuracy and time spent on one iteration rather than on its convergence rate, on the improvement of which algorithms modifications are in most cases focused on. As PSO algorithm requires parallelizable computation of goal function values for all particles on each iteration, and that such recomputation requires solution of the direct problem, to perform the computation faster, we propose the following algorithm for running it on GPU. For each particle of the swarm, we allocate a group of threads that coordinatively solve the direct problem. As the most time-consuming part of the solution of time fractional differential equation is the calculation of non-local part of fractional derivative, we map each thread in the group to a node of finite difference grid and perform parallel within each group computation of non-local part making use of the local memory or GPU. Then, other step of direct problem solution is performed by a single thread. The movement of particles using the recomputed values of goal function was performed on central processor, and its influence on total execution time is negligible. The GPU algorithm was implemented using OpenCL framework. For comparison purposes, we also considered multi-threaded implementation on central processor using OpenMP. In CPU implementation, each thread executed computations related to a single particle. We performed two series of computational experiments. The first one to test the accuracy and the second one to test the efficiency of GPU implementation regarding solution time. To simulate possibly inaccurate field measurements, we generate testing datasets in the form of noise solutions of the direct problem. So, for fixed values of physical parameters and randomly generated set of fractional derivatives orders, we solve the direct problem, randomly select a given number of grid nodes as observation points, and add the uniform random noise to the modeled values of water head and salt concentration of these points to simulate measurements and accuracies. In such a way, we obtained a series of data sets with 4 parameters. 2 values of fractional derivative orders, a number of observation points, and a level of noise. The example of the resulting testing dataset is presented in the current slide. To check the accuracy of PSO algorithm usage for parameter identification of the considered model, we send the generated datasets as inputs to the PSO, further analyzing relative errors of fractional derivative orders restoration depending on other dataset parameters. The experiments were performed on one node of the cluster of the Institute of Cybernetics. As the result, we found that the orders of non-local time fractional derivative is restored with 10 times higher relative errors when compared with the errors of restoration of the order of local space fractal derivative. Errors expectedly increased with the increase of noise level and non-uniformly depended on the values of derivative orders. We also determined the minimal number of observation points needed to obtain practically usable accuracy. This value equal to 25 points. Studying execution time, we checked the influence of the number of particles in the swarm, the size of the grid, and the ending simulation time on the performance of GPU and CPU implementations. As not all computational resources or GPU were used in our experiments, execution time of GPU implementation did not depend on the number of particles, while for CPU implementation it linearly increased for the number of CPU cores less than the number of particles. Execution time of the both implementations increased linearly with the increase of the grid size. GPU implementation in this case was slightly faster for 10 particles and 50 nodes in the grid, with the tendency of speed-up increased with the increase of the grid size. When observations in a longer period or a lesser time step are used, execution time quadratically increased with the increase of the number of time steps. Expectedly, having the same order of computational complexity, as computations are parallelized only on a single iteration, GPU implementation has 5 times lower values of highest power coefficient in the corresponding dependencies. All the obtained results were in perfect agreement with theoretical expectations. To conclude, I can say that our study confirmed the efficiency of particle swarm algorithm application for parameter identification of fractional differential model, applying it to filtration consolidation model that contained both non-local and local fractional operators. For the considered problem, we determined that the order of the non-local derivative can be restored by the proposed procedure with lower accuracy comparing with the order of the local fractal derivative. We also experimentally determined the minimal number of observation points needed to obtain a fairly acceptable level of accuracy. With the combined use of the features of both the PSO algorithm and the numerical method of the direct problem solution, the GPU algorithm was developed. It showed in our computational experiments up to 4 times higher performance when compared with the multi-threaded implementation. Thank you for your attention.